So we have post on our Facebook group, Electronics Technician, Hobbies and Engineering. So this is about uh, transistor. So here, so this is by Godwin Saldoa. So he asked, "Help! Can someone tell me how is this NPN transistor in saturation mode? I thought it's supposed to be in forward active mode. If VBB, he's talking about this one. I think he mean about VDD, which is the 9 volts, is less than the VCC, which is the 12 volts. So in here, so on the simulation, you get a beta of 100 saturation, which is in saturation NPN. And I think this one would be the IC is 2.49 milliamps, and IB is 234.73 microamps. And the base emitter voltage is zero point 0.6 or 623.16 millivolts or 0.623 volts. And voltage collector emitter voltage is 68.5 millivolts. So if the voltage collector emitter voltage is less than the voltage base emitter voltage, the transistor is in saturation mode. So the base collector also is 554.66 millivolts. So this is his schematic. So the 9 volts, 800 ohms on the base. So 12 volts supply with 1.K resistor on the collector and the 3K on the emitter to ground. So what I'm going to do is I'm trying to calculate this one to see if the transistor is in saturation mode. And let's get started. So here I'm using a genuine BC337 NPN transistor, and on the datasheet it says the maximum collector voltage is 45. So the HFE also 200, collector current is 0 0.8 amps or 800 milliamps. So here we have 199. So the base emitter voltage is 0 0.743. So this is the only transistor that I can get closer to 100 beta. So we'll use this one for our demonstration purpose today. Okay, let me draw the schematic. So here we have the RC, which is equal to 1.5K. We have the RE, which is equal to 3K. Here we have the RB, which is equal to 800 ohms. So our base emitter voltage will make it 0.74. So here is our IE, IC, IB, and this is our VCC, which is equal to 12 volts, and also the VDD, which is equal to 9 volts. Okay, first is we need to find the voltage of RA across this resistor here, the BRA. So our RA is equal to the voltage from the VDD minus the voltage drop across the resistor RB and the voltage drop across the base emitter voltage. So which is equal to VDD minus the voltage drop across the resistor, and using Ohm's law the voltage drop across the resistor is equal to IB times the resistor RB minus the V base emitter voltage, so 0.74. So we'll substitute that one later. So since our IC or IE is approximately equal to IC, and also IC is equal to beta IB, so the collector current is equal to the IB multiplied by the beta. So for this one we have this BC337, which has a beta of 200. So we use that beta later on. Now, so if we find the value of IB, this one here, so IB is equal to IC, because or IE, because IC and IE is the same, so we say IE divided by beta. Now from our original equation here, equation 1, so we have the voltage RE, or the voltage drop across here. So the voltage drop across RE in using Ohm's law is also equal to IE RE. So this voltage drop across RE is equal to IE times RE. So we equate this one, VDD minus. So now our IB is equal to IE over beta. So we have this IB over beta times RB minus base emitter voltage. Now we have to transpose this equation. We make our this is IB, this is IE. So we transpose this equation. We place the IE values variables in the left and the rest will be in the right. So we have this RE plus IE RB divided by beta equal to VDD minus base emitter voltage. So now we have common variable for this function here. So we take the common of this function, which is IE times RE plus RB divided by beta is equal to VDD minus BE. Now we can simplify this function here with common denominator of beta. So we make beta times beta RE plus RB is equal to VDD minus BE. Now we move this equation to the other side. So in order to have only the IE on the left, so we make this one as VDD minus BBE divide by beta RA plus RB. And then close parenthesis, we multiply this one by beta, the beta to the other side. So now we have this IE. Now we trying to calculate. Now we're trying to calculate IE. So we substitute the VDD, which is equal to 9 volts minus 0.74 times 200. So divide by 200 times RA. The RA value is RA value is equal to 3K plus 800, which is the RB. So do you have a calculator? Try to calculate this one. So 9 minus 0.74 is 8.26 times 200. Then divide by open parenthesis 200 times 3K or 3 exponent of 3 close bracket plus 800 close bracket equals. So we have 2.749, so we round it off to 2.75 milliamps. Now we try to calculate the voltage drop across the emitter resistor RE. Calculate VRE and VRC. So VRE is equal to IE RE, which is equal to 2.75 milliamps times 3K. So VRE, so 2.75 exponent 3 negative times 3 exponent of 3. So we have 8.25 volts. So now our VRC, which is the voltage drop across this resistor here, which is equivalent to IC times RC. So since our IE is approximately equal to IC, so our current is 2.75 milliamps times RC value is 1.5K. So our voltage drop across RC, try to calculate 2.75 exponent of 3 negative times 1.5 exponent of 3. So we have 4.125. So now what's our voltage saturation? The voltage drop collector emitter voltage. So our voltage saturation or V collector emitter voltage. So our V collector emitter voltage is equal to VCC. This is the voltage on supply voltage minus voltage drop across the RC, and then minus the voltage drop across the RE. So our voltage collector emitter voltage would be 12 volts. Our RC is 4.125. Sorry, 4.125 volts. minus our RE is equal, VRE is equal to 8.25, 2.5 volts. B, collector emitter voltage is equal to 12 minus 4.125 minus 8.25. So we have negative 0.375, which is saturated. So when voltage collector emitter voltage is less than the voltage of the base emitter voltage, transistor is saturated. So anyway, if you want to calculate the base current, so IB from our first equation here is equal to IE over beta, which is equal to 2.75 milliamps divided by 200. So 2.75 exponent of 3 negative divided by 200. So we have, 2.75 exponent of 3 negative divided by 200. So we have 13.75 microamps. So, and our voltage drop across RB is equal to IB times RB. So voltage drop across RB is equal to 13.75 microamps times 800 ohms. So the voltage drop across RB times 800, so would be 0.011 volts. So if you equate this one again, if you prove this one, that our voltage across RE is equal to VDD minus VRB minus base emitter voltage. So VRE is equal to 9 volts minus 0.011 minus 0.74. So 9 minus 0.011 minus 0.74. So we have 8.249 volts. So which is equivalent to 8.25. So now we have to prove this equation by building the prototype or the breadboard. Okay, for our transistor that we're using, so we have this collector, base, and emitter. So okay, here we have the breadboard. We breadboard the circuit. We have the BC37. So this is our base resistor, 800 ohms, and this is our 3K, which is the emitter resistor, and this is our collector resistor. So based on our calculation, so I only have 820 ohms. I don't have 800 ohms. If I need to exactly find 800 ohms, we likely to get the exact calculation or value that we get from our calculation. So, so if we measure the emitter voltage, so we have 8.21. Our calculation is 8.24, 8.25. So we're very close. So our base emitter voltage, which is this to here, we have 0.65, and our collector voltage would be across the RC. So we have a 3.78. So our calculation is 4.125. So the voltage drop across the base resistor would be negligible. So we have 0.19 volts, and the saturation voltage, collector emitter voltage, would be 0 here. So our calculation is correct, and it proves that the circuit that we measure is exactly what we are calculating. So I will see if we can get exact 800 volts, 800 ohms, and we'll see if we get it exactly right on the, but not quite, because I'm assuming that the 0.74 volts across the base emitter. Any variation on the applied base current will also change the voltage across the base emitter voltage. So I think this would be good enough, and thanks for watching, and I hope you find this one useful, and I'll see you next time.